Welcome back. Today I will see some example of maximal and prime ideal. This is our goal of today's lecture. I have told you many times this type of concept actually very important for any competitive exam, also for higher study. Today I will say for which of following ideals they are prime and maximal ideal. Option 1. The polynomial x minus a contain R of xy where a belongs to R. Option 2. 4, 2x minus 1 contain zx. Option 3. I will see ideal which is generated by 2 plus 2i. I will see this ideal is not prime ideal of Zi. Also I will see how many elements contain in the quotient ring Zi modulo I and what is the characteristic of Zi modulo I. This is our goal of today's lecture. First I will say is the polynomial x minus a which contain in Rxy. Is this maximal or prime ideal? For this, first the ideal x minus a which contain in Rxy, is it maximal ideal or prime ideal? For this, if we consider the quotient ring Rxy modulo ideal generated by x minus a. Obviously, this means the set containing the element fxy plus ideal generated by x minus a where fxy belongs to Rxy. Ideal generated by x minus a means obviously x minus a plus ideal generated by x minus a. We write this as 0 plus ideal generated by x minus a, and that imply obviously x minus a equal to 0, that imply x equal to a, and since x equal to a, therefore Rxy quotient ring ideal generated by x minus a is isomorphic to Ry, and obviously this Ry is an integral domain. So since Ry is integral domain, so obviously Rxy modulo ideal generated by x minus a, this ideal is prime ideal. Since this is the integral domain, and we all of us know Ry is not field because here Ry is integral domain but not field. Here every element has no multiplicative inverse. So obviously this ideal not be maximal or ideal, not maximal ideal, only prime ideal. So Rxy modulo ideal generated by x minus a, obviously this quotient ring which is isomorphic to Ry, obviously this ideal x minus a is prime ideal, not be maximal. Our ideal. Second example, zx modulo ideal generated by 4, 2x minus 1. Obviously this means fx plus ideal generated by 4, 2x minus 1 where fx in zx. Here similar to before, ideal generated by 4 comma 2x minus 1. Ideal generated by 4 comma 2x minus 1 means obviously we can write 4 comma 2x minus 1 plus ideal generated by 4 comma 2x minus 1 equal to 0 plus ideal generated by 4 comma 2x minus 1. That imply 4 equal to 0 and 2x minus 1 equal to 0. And by this together we can tell obviously 2 equal to 0. And since 2 equal to 0, that means 2x minus 1 equal to 0 times x minus 1, and this imply minus 1. This is equal to 0 minus 1 equal to 0. And since I have got minus 1 equal to 0, that means that imply, since minus 1 equal to 0, that imply 1 also equal to 0. That imply 1 equal to 0. And since 1 equal to 0, that means zx modulo ideal generated by 4 comma 2x minus 1. This is isomorphic to only. Since 1 equal to 0, that means obviously this is isomorphic to only 0. Okay? That means this is isomorphic to only unit ideal. No, this is isomorphic to 0. Therefore, this is not integral domain, not field. So, since this quotient ring is isomorphic to only the set 0, and since this is not integral domain, not field, that means obviously this ideal be not prime ideal, also not maximal ideal. Okay? I hope my all viewers have understood this is clearly. This type of concept actually very important. If you can understand this question easily, then you can verify any question, any type of question easily. Here only method is, since in this question ideal generated by 4 comma 2x minus 1, that means this imply 4 equal to 0 and 2x minus 1 equal to 0. Since 4 equal to 0 and 2x minus 1 both equal to 0, that means 2 equal to 0. So, we can verify this quotient ring is isomorphic to which ring easily. And then to understand this method easily, then you can solve any question. So just pay attention. 2 plus 2i is not prime ideal because 2 times 1 plus I equal to 2 plus 2i. But neither 2 belongs to 2 plus 2i nor 1 plus I belongs to 2 plus 2i, because if 2 belongs to 2 plus 2i, then 2 equal to 2 plus 2i times a plus bi. Okay? That imply 2 equal to 2a minus 2b plus 2a plus 2b times I, where for some ab belongs to integer. That imply if 2a minus 2b equal to 2 and that imply 2a plus 2b equal to 0. That implies by solving this equation a equal to half. But a equal to half cannot possible because here given ab belongs to integer. That means 2 does not belongs to 2 plus 2i, the ideal 2 plus 2i. Similarly, if you can say 1 plus I, the element 1 plus I does not belongs to 2 plus 2i. Okay? Therefore, since we can write the ideal 2 plus I, we can write this as 2 times 1 plus I. But neither 2 belongs to 2 plus I nor 1 plus I belongs to 2 plus 2i. So, 2 plus 2i is not prime ideal. I hope my all viewers have understood. My next question. How many elements exist in the quotient range Zi modulo ideal generated by 2 plus 2i? Zi modulo ideal generated by I means we all of us know a plus bi plus ideal generated by 2 plus 2i. We all of us know if we write 2 plus 2i plus ideal generated by 2 plus 2i, this is obviously equal to 0 plus ideal generated by 2 plus 2i. That means 2 plus 2i equal to 0 and that imply 2 equal to minus 2i. Just cancel 2, that imply y 1 equal to minus I. If we square both sides, then that imply 1 equal to minus 1. That imply, since 1 equal to minus 1, that imply 2 equal to 0. Therefore, if we write one element such type 9 plus 8i plus ideal generated by 2 plus 2i. Since I have got 2 equal to 0, that means that imply 9 plus ideal generated by 2 plus 2i, and 9 means we can write this as 8 plus 1 plus ideal generated by 2 plus I, and 8, since I have got 2 equal to 0, that means obviously 8 also would be equal to 0. Therefore, the elements 9 plus 8i plus ideal generated by 2 plus 2i, this is equal to actually 1 plus ideal generated by 2 plus 2i. That means here the elements are look like a plus bi plus I, where a belongs to 0, 1, 2, 3 and b belongs to 0, 1. Therefore, there exists a distinct element. Okay? I hope my all viewers have understood the question. Okay? How many elements exist? How we have to find the element? Okay.